Hello and welcome to MVP Days. My name is Alessandro Goncalves and I'm going to talk about disk speed. You may ask yourself what's disk speed? I hope not. I hope everybody knows what disk speed is, but it's a IO generator tool for Microsoft Windows, and it is the main tool used on the Microsoft side of the world to generate IO test benchmarking. There are other tools like IOmeter or FIO that do run in Windows, many others as well. So it's really nice to understand how disk speed behaves. So we can change those behaviors when we think we can squeeze more performance out of a test or comparing to other tools. Sometimes other tools doing basically the same thing generates more favorable results. It does not tell that the one tool is better than the other. It's just that the behavior of each tool is a little bit different. So let's get going. That's basically my only slide for the session. So I hope we can talk 30 minutes of only disk speed. I hope I can do that. So we're going to talk about affinity behavior. So affinity behavior is basically when do threads run. So let's start that with going to our desktop. So I have a Dell desktop with two NVMe devices. Um, Here you can see that I have 12 logical processors, 12 LP, one socket, and hyper threading enabled. So basically, I have 6 cores, 12 thread running, could be running simultaneously in this machine, but uh, remember, I have only 6 cores in this setup. Here I have just a small performance monitor with some counters that can help us look at the behavior behind the scenes for a while. So let's go for our first disk speed of the day. So I'm running disk speed. As we all know, 30 seconds, 4 threads, block size of 4K, outstanding I/O. So our kill depth per thread will be 16. 0% write, random access pattern. L will be our display our latency, and here I'm controlling the cache, so I'm disabling software and hardware caching. So I'm going to do a write through, um, and let me change that because this is going to be for our second test. So the affinity behavior of disk speed is to fill up in sequence our logical processor. So in this case, I have 4 threads and I'm using the very first 4 logical processors. Here we have the IOPS, so these transfers per second. We are doing 107K, 108K per second in this test. Right? The number per se does not matter much. If it's good or bad, can we get more? But I'm more interested on the behavior. So we saw this behavior. It is constant, like I mentioned. Each thread, 4 threads running on its own logical processor. What happens here is that since I have 6 cores, I could tell, right? I would need to use another tool to tell you that, like CPU info, but I can tell you that the first 2 logical processors are bound to first core, second core, third core, fourth, fifth, and sixth. So in this case, the first 2 threads are running on one core, the thread number 3 and 4 on the second core. So I have actually 4 cores that are not doing anything. So if I disable or control this behavior, I could do a better job. So in this case, remember that we're doing 107, 108 thousand IOPS. So if I use the -n, this disables the default affinity of disk speed. So pay attention on how the CPUs are going to behave, and pay attention how much more IOPS I can generate with the same test. So what happens is that I'm taking advantage of the free cores. So most likely those threads are running in different cores or free cores. So I'm not saturating each LP, and I'm generating more IOPS. If I care more about the IOPS, that's kind of what we're going to see. So that's the completely different behavior from the other part. Just to and if you want to control where the threads actually are going to run, you can use the dash AG. So the first one's going to be our processor group. In this case, I have only one processor group, and I'm going to ask them to run on different LPs. So let's say 0, 2, 4, and 6. So 0, 2, 4, and 6. 6. So 0, 2, 4, 6. Core 1, core 2, core 3. So in this case, I'm manually asking to run on different cores. So it's always going to have in one thread per core. So to see if we can get a running performance. So you're going to see that the CPU graph are not going to change much. It's going to be a flat line because I'm using that LP directly. And I'm running on each one of each core. You see that the number of IOPS is basically the same as before. So let's see, before we have about 149,000, 150,000 IOPS. And we can see how much we got here. Basically the same. So in this case, controlling the affinity, it is something that will get you better results sometimes. So it's not that you have to disable that. We have to understand if there are more cores that are not going to be used. Sometimes if you want to push more numbers, um, maybe controlling that affinity where the threads are going to run, it's a good alternative. Otherwise, if you're using all the LPs, you're going to have that. You don't need to change the affinity, but if you want the uber best performance, maybe you just make sure control the affinity to run one thread per core, so you don't have two threads um, be on the same core, so disputing resources. So talk about another tool for I/O. We have our famous I/O meter. So in this case, I put uh, on D drive just to make sure we are going to the D drive. Yes, and 16 outstanding. So I set up 4 workers here, and let me push here, and let's start save. Let's see. We do have here 154, 156. So we're doing a little bit better here. And if you look the full behavior of I/O meter, it is basically uh, the same as no affinity. So it will let the operating system decide in which core it's going to run. And obviously I'm using the same number of threads as the disk speed. So you could ask, why do I have a better number here? That's really a cool thing. Do do we have the same block size? Yes, we do. So let's see access. So 4K, 100% read. But look, we have 0% random. And here we have random. So comparing that, you can see that the different types of setting will give you. So we want to make sure that we are on the same boat here. So that's the good thing about comparing tests, is that you have that. So I hope you understand what I'm talking about, the affinity part. And you can look at how much difference just changing those switch, changing those behaviors could get you, either for a better result or a worse result. So testing and manipulating is a important thing to use. So our second feature today is caching behavior. So caching, there are a lot of caching involved in Windows and storage. We have the file system caching, you have the storage controller caching, we have the SSD caching. So that's a really important thing to understand. What are you doing here? So um, one parameter to, let's go to the default test, one parameter to control caching, it is the SUW. So that's basically full write through, no software caching. So if you look at the beginning of a uh, display of the disk speed, it tells you if you have the software cache disabled or hardware write cache disabled. So if you're talking about the operating system cache, you're going to see changes in memory. So are going to use more memory, less memory. So if you're using caching on the file system, you're going to see that your available memory may decrease. Your standby cache may increase. So let's see if there is any change here for the caching. We have some cache also. You don't see any dirty pages or any other major change that would uh, force you to go and say, well, I'm using. So we can kind of prove, okay, that settings is working. So now let's say I'm going to use software caching. So let's start looking at this. See, our copy reads per second on the cache object starts to uh, go up because I'm reading these to the software cache. But look, basically the same test, but look our IOPS. So it kind of tells you, look, caching in this case, it is much worse than no cache. I really have a really fast disk, so why do you bother using cache? So that's one of the reasons why we tell, well, we're doing a file copy and to test our storage. That's the worst thing you can do because you're actually file copying. You're just using a single thread and also using the file system cache. Another cache behavior that you can control with disk speed is what we call mapped, memory mapped file, which with the M. So in this case, you're going to see that our file, which is basically a 50 gigabyte file, it's going to start taking memory space. So if you look at this, uh, graph or here on available memory, you're going to see that it's going to start decreasing because I'm pushing pages or using memory pages to uh, fill up with the data from my file. So you see here how we're going to start decreasing our available memory, but we're not using much of the file system cache. So this is not the file system cache. It is actually using RAM for memory mapped files. So in this case, also it's better than the file system cache, but way worse than my NVMe. So that's another case that where caching behavior, it is very important to understand how we're doing that, because that's a thing that will disrupt your testing. If you're doing storage testing, you don't want any type of caching. And luckily for us, once the test finishes, my available memory goes back to normal because we are not using that. So caching, control caching behavior is important in that sense because we sometimes we want, sometimes we don't want to use cache. So you want to understand what's your testing metric and what you want to test. So in this case, we prove that accessing memory from the operating system is actually slower than accessing a persistent memory or our SSDs, NVMe SSDs in a multi-thread scenario. So it's always how you're comparing. So when you're looking benchmarking, you really need to understand uh, what are the parameters that you're testing. So that's for caching. And another thing that we have is completion ports. And that's how, when we're creating I/O, we can have a pool of threads using completion ports. So a good explanation is actually looking at our GitHub page for DiskSPD on our wiki and cust our parameters, and the x-x is our completion ports. So by default, it is going to use completion ports, which is the most efficient way to use, right? So uh, I would say most of the time or all the time, I never had to disable that uh, for any reason. But I had a case where people were using another very famous tool for doing benchmarking, and it was way worse than DiskSPD. And by just debugging, I'd say, well, you're not using completion ports. So let's see the difference here. So remember that you're using, we're having like 150,000 IOPS. So let's disable cache and disable completion ports. Well, you're having 150,000 IOPS with the Affinity disable, right? So just to be fair, let's disable Affinity and do it again. So a little bit better, but you see that we do have. So if you're doing a really high performance testing, not using completion ports will have a very bad effect on your testing. So by default, DiskSPD already using the completion ports. You don't have to worry about it. But if somebody asks you or you're seeing behavior that it is not what you expect. Like people, look how bad Windows is because I cannot get the same thing that I get on Linux. And you look on Linux, they have their own completion port idea, and when they port the tool to Windows, they don't use completion ports, for instance, and that creates a different result behavior. And what happens? People just badmouth on the Windows part because, oh, look, I'm using the same tool and I really have a really great result in Linux and a not so good result in Windows. And most of the times, settings are not okay, and or they using um, different number of cores, threads, and completion ports, and, or not using completion ports on Windows. So very important to look at it. So let's move for that. That is what I wanted to talk about completion parts. Just making sure that if you're comparing to another tool, that the other tool is actually using completion ports, or you want to go and I can make a disk speed to run slower, so I disable completion port, and now everybody is slow. Of course, you don't want to do that. Burst IO. Wow, versatile, or what I call checkpoint behavior. So when we're doing a test or a benchmarking test, um, the behavior is artificial. It's a synthetic benchmark, like they call, because I'm always throwing IO. I always have keep that high, and that's not how the real world behaves. If you work with databases, you see that we have from time to time a checkpoint, or either from time to time, or the amount of dirty page that we have in memory that we have to commit to disk. So you have those peaks and valleys. So, and that's the point. Starts not working, and then out of sudden you have a burst of IO, and then we have to not, and then we don't have any IO for a while, and then it repeats endlessly. So it's not fun sometimes. So let me just remove the completion parts here, or uh, add the completion parts back. So to create this scenario and this speed, you can use -I, which is how many IOPS you want. Let's say I want for each burst, I want 85,000 IOPS. And for how long? What's the wait time in milliseconds? So let's say every 5 seconds, so 5,000 milliseconds. And let's see how it behaves. See how we have spikes and then 0, and then so well, have more spikes. So that's kind of where in the real world we see mainly databases doing that. They're not doing much, and then all of a sudden you see, and you see the CPU utilization as well. So it's very spiky in this case because that's kind of we have some work to do. We do that work, and then we don't do anymore. Obviously our IOPS here is like 14,000 in average because that's kind of the average that you're getting. So why we do that sometimes? Because sometimes you want to test how fast that storage is going to respond that amount of IOPS. The only thing that you have to realize, do you have enough either threads or cube depth in order to generate those 85,000 IOPS? Because what we could do, it is, let's say, every 2 seconds, let's try to do 400,000 IOPS. And let's see how the disk is going to behave. See, NVMe is so good that we don't even create much of a queue. Of course, this object, this counter is every second. So every second I take a snapshot. But we're pushing, and then the NVMe drive just eats those IOPS. It is much fun. But things that, see, we increase our IOPS per second, but things that we need to look at, it is how fast, what's our average latency, because that's the most important thing. So in this test, our average latency is like half of a millisecond. On the previous test, where we get, so you can look that average latency didn't grow much, which is good. So it means that we could throw more IOPS. Other metrics that we look is our KOS, our quality of service. So 3 nines, we are on the millisecond, 1.5 millisecond. So let's compare 1.5 milliseconds with 3 nines here, 3 nines, 1.4 milliseconds. So basically in the same ballpark. So what that tells you is how many IOPS you want per burst and what's your quality of service. Because the storage will process the IOPS. It's just how fast you want that to be processed. So that's kind of where we are in this sense. So that's what I call burstiness of IOPS. So last part is you can use DiskSPD to capture things with WPR, which is our Windows Performance Recorder. WPR, it is already here in the operating system, the new, so just WPR, and then you do start. And you choose, so with DiskSPD, it comes with a profiler. So if you do the IR here, you can use DiskSPD.wprp, which is the profiler that you want to use. So if you want to capture specific disk speed settings, you can just use that. So WPR, and then we're going to start a capture. We're going to use disk speed WPR, bang, disk speed. And then we have two modes, or either light or verbose. Light should be fine, and then you just work. So let me start the capture. Obviously, I don't have permissions. So let's open with administrator. Here I am. And actually, we can just point. So let's see if I go to another drive. I have a captures folder here. I can use WPR and start, and I can just point to the these will only capture disk speed related acts, so you're not going to see much on the performance analyzer. So if you want to add another profile, you can just add start, and then let's say disk IO. And here I have WPR starting to collect disk I/O. So let's run again our test with burstiness. So everything that it goes through. One thing that you want to look at is that any type of tracing will affect your performance. So you're not tracing to discover raw performance, you're tracing just to discover the behavior because every time you look, you inject latency, and that's how it is. So I'm going to stop the trace now. PR, stop, and I can give a name, MVPDays, ETL, and it's going just to create a ETL file. And sometimes it takes a long time, so I'm going to open one that I already created. So it's already there, so that's good. It's already created. We could actually open that one, so let me cancel that one. And the performance, this performance analyzer. Now let's open our MVPDays. And I want to show you what that capture actually gives you. And it's opening. So like we'd expect, since we're having burstiness, we have these peaks and valleys on our storage. So disk speed related, it's going to be in these regions of interest, which is just the runtime for disk speed. And then start stop. So that's kind of what you see. If you have other, let me pick here, thread activities. Same thing as so sometimes it will show you a cooldown period. Let me open another one here, which is much better. Let's choose disk speed burst. It's basically the same command with burstiness and other things. So that's what I'd like to show you. Well, if we're going to talk about the PA, we are going to stay a long time here talking about, but just things that we can look at very briefly. And done. So we can speed it up. System activities. And let me see this guy. It's not it. Here it is, regions of interest. And loading. See how computation is. Come on. So hopefully when it opens, we're going to see the cooldown period, the runtime, and the warm-up, which are the three phases of disk speed where we either have capture or of latency, but we still have disk perform or disk activity, and some we don't have disk activity, which is the warm-up period and cool down. So um, let's see if we can open this to give you a better vision. Here we go. So here we have the warm-up period, the whole disk speed I/O, and the runtime and cooldown. So we have the warm-up at the beginning and cooldown at the end. And if we want to see if there is any I/O activity, what we can do, so where we have I/O activity or don't, is to match like disk usage on the same. Let me do disk utilization by disk. And let me just do disk speed filter. And see how we have this. Let me do this. And then we have the IO type happening here. Reads. And 4 threads, we run 4 threads. And we can go on and on. So each thread is going to have all the IOs that you have, priority, and so forth. But what I want to show you is that even on the warm-up, and here we do have some IO activity. Let me just do, let's see if I change this. But that's kind of what I would like to show. So 7 minutes past the hour or passing the time. Hopefully you enjoyed what I had to show you. So some takeaways. Pay attention on affinity. It's very important. Small details will lead to different results. Cache memory bottleneck on fast devices like NVMe. So can be a bottleneck. So sometimes you do need cache, sometimes you don't. So it depends on the test. And obviously understand the behavior and that what's going to make sure you're using same testing functions and everything. So you're actually comparing, like they say, apples to apples. Thank you very much. It was a pleasure. If you have any questions, just you can shoot me an email or better, just join the Azure Stack HCI Slack group. Thank you.